Hey guys, today we're actually going to conclude the energy unit. Before we actually do that, I wanted to just go over quickly the homework from last night. So let's start with number one. Which graph best shows the length of a shadow cast from sunrise to sunset by a flagpole in New York State? So I don't know if you remember, but we said when the sun is directly overhead, that means when the sun is highest in the sky, you get the shortest shadow. And that happens at noon. And then the longest shadows are when the sun is lowest in the sky. That would be as the sun is just rising above the horizon or setting. So if you take a look, looks like choice C looks not good. That's the opposite. Choice D looks like the right choice because at sunrise and sunset, you have the longest shadows, right? And at noon, you have the shortest shadows. So that's choice D. Number two, to an observer in Pennsylvania, the sun appears to rise each day. Again, remember I told you I don't care whether they say Pennsylvania, New Jersey, New York, anywhere in the US, we all work the same way with the sun. The sun will always rise somewhere in the east. So you should have gotten choice C for number two. Number three, the diagram below shows the noontime shadow cast by a vertical post located in New York State. Which letter indicates a location west of the post? So they're talking about noontime, right? At noontime, I don't know if you remember, but we said the sun is always to our south. And if you take a look here, you can see the shadow here. Well, if the sun is to our south at noon, this has to be south because the shadow would be in the north, right? So that would be north, that would be south, and then you just kind of got to imagine this as a compass. If I were to flip this around like that, this would become east, and you could find the compass on page 3 of the reference table. This would then be west. So choice B is west of the post. For number four, the diagram below shows the noontime shadow cast by a vertical post located in New Jersey. Again, I don't care where they say, as long as in the US, it works the same way. Which letter indicates a location south of the post? This picture in number four, doesn't it look exactly like number three? So again, it works the same way. North, south, east, west, and they wanted south of the post. Well, here you are, south of the post, choice A. On which two dates could all locations on Earth have equal, and the key thing here is equal, equa, and for all locations to have equal hours of day and night, 12 hours of day, 12 hours of night, that would have to be on the equinoxes. So choice D are the equinoxes. Number six, the diagram below indicates the amount of solar radiation that is reflected by equal areas of various materials on Earth's surface. Which material absorbs the most solar radiation? So look, they show you the incoming rays, and then they get absorbed by the ground somewhat. And you can notice the forest and the grassy field, they are darker. So then they show, it says here, it indicates on this diagram the amount reflected. So the less reflected, the more absorbed. And I think I even told you that the best reflector on Earth is a forest. And you can see a forest only reflects 3 to 10%, meaning that it reflects somewhere between it absorbs somewhere between 90 to 97% of the sun's energy. The best reflector on Earth is, remember I said a snowy field or a glacier, because it's light color, it's a smooth texture. So if they were asking about the best reflector, look at that. The fresh snow reflects anywhere between 75 and 95%, by far the most. But here they're asking which absorbs the most solar radiation. That would be your forest. Under identical conditions, which surface will reflect the greatest amount of insolation? Like we just said, it's either snow or a glacier, glacial ice sheet. And lastly, they give you a group question here. They give you two pictures. I could read this whole thing, but the key thing to know here is this is at different latitudes in the northern hemisphere in winter. So here's a clear sky, here's a cloudy sky. Approximately what percentage of the insolation actually reaches the ground at 45 degrees north latitude on a clear day? So I would have to go to a clear sky, and look what it says. It's right there on the picture. 80% reaches the ground. 80% is your answer. So for this, for number 8, you should have gotten B. Which factor keeps the greatest percentage of insolation from reaching the Earth's surface on cloudy days? So I'm going to go to a cloudy day, and look here. I don't know if you guys could see it, but cloud reflection. You see those rays getting reflected by the cloud? So up here, way up here, the scattering reflection is only 6%. But right here, look at that cloud reflection. On a cloudy day, that's why it's colder, 30 to 60% of the incoming energy from the sun is reflected by the droplets in clouds. So there's your answer. And according to the graph, on a winter day at 70 degrees north latitude, what is the approximate percentage of the insolation that is reflected? And you can see here it says average reflectivity, degrees latitude. They mentioned 70 degrees north. So I'm going to go to 70 degrees north. It looks like it's right up here, 70 degrees north. And as I slide over, oh, that is not a straight line, but it's somewhere between 80 and 90%, and 85% is your answer. Hopefully you didn't have a problem with that. Now let's get into the last thing we need to know about, global warming and the ozone effect. And right now, that is a very hot topic, no pun intended. Okay, take a look. Temperature changes over a day. So the first thing I want to show you is a graph. And this is a graph that shows you temperature and energy versus time. Now, how do I know this is showing over a day? Because look, it starts at 12 a.m. Here's noon, and all the way back to 12 a.m. That's 24 hours. So just look at this graph. There are 2 lines on the graph. There's this dash line, and I even show you on the graph, and you'll get this on a test. Insolation, the amount of incoming solar radiation. So the first thing we need to know is, when is the greatest intensity of insolation during the day? Well, we already know that because we said it's when the sun is highest in the sky. But in case you weren't sure, there is the peak insolation, which happens at noon. So that would be noon. Now, when does the highest temperature generally occur? Well, you would think if the amount of insolation is greatest, this is the greatest energy of the sun, you would think that would be the maximum temperature. But take a look here. It's not. In fact, they even label for you when you have the highest temperature or the hottest time of day. It's right here. Slide down, and the hottest time of day always falls between 2 and 4 o'clock p.m. in the afternoon. The lowest temperature would be the coldest time of day. And if you take a look right here, it falls between 6 and 8 a.m. That would be sunrise. So why does that happen? Well, here's why it happens. You got to think back to that picture we looked at where you have the UV rays coming down from the sun, and then the energy is absorbed by the ground. And we said a good absorber is a good radiator. So at noon, you're basically getting hit with just the energy from above from the sun. You're basically getting hit with the short wave radiation. Oh, this is daring. This is very daring of me, but let's try it. Short waves going down from the sun, right? Oh boy. Hitting the ground, right? We'll make this the ground. Oh. And then the ground is absorbing the sun's energy for hours, and it's building up heat. It's just building it up. And a good absorber is a good radiator. So at noon, you're getting all these short waves, the UV, and it's heating up the ground. And eventually, it gets re-radiated later in the afternoon between 2 and 4 o'clock back to space. And that is why, and by the way, those are longer wavelengths. That is infrared. I'm going to put IR for infrared. Oh, that is not working. IR, whatever. I'll put the R underneath. There we go. Bad R. Bad R. So at noon, you're just basically getting hit by this. But give it 2 to 4 hours after noon, and you're still getting hit with this, but now you're getting hit with an uppercut too. So just imagine a boxer. Boxer getting hit with like a left hook. only, not that that feels good, but a left hook, and then give it 2 to 4 hours after noon. You're not only getting hit with that left hook, you're also getting hit with an uppercut, and that you will feel more. So that is why we feel more of the sun's energy 2 to 4 hours after noon, or in other words, 2 to 4 p.m. So this happens because the sun's rays are absorbed by the Earth's surface and re-radiated back to space during the afternoon and night. Now there's another graph here. It looks very, very similar, but you're going to see something here. There's an extra line in the graph. And take a look at the time scale. Instead of 12 a.m. all the way around to 12 a.m. one day, now you're talking about the months, starting in November, working 12 months to next November. So this is going to be how temperature changes over a year. Now you got to look real carefully, but they even mark it for you. Here's insolation, incoming solar radiation. And when would the greatest intensity of insolation occur? It would occur right here. And look at what date. That's no surprise. June 21st, right? That's when the sun is at its absolute highest in the sky here in the northern hemisphere. And that is why we are getting the greatest intensity of insolation on that date. So then we're going to go to the temperature at Earth's surface. And we want to know, when does the highest temperature occur? And you know what? I would expect it to be June 21st. But we know here in New York, that's not usually when it's hottest. Follow it carefully. It's a little bit hotter right here, the end of July or the first week of August. That happens to be 6 weeks after June 21st. The reason is, again, think back to that picture I drew on the last slide. For a good 6 weeks, you're getting all of that energy building up, being absorbed by the Earth's surface. And then take a look. See this re-radiation? Those are the infrared rays. A good absorber is a good radiator. Look at that. You hit the maximum re-radiation right here. Combine that with a pretty high insolation, and you get a hotter temperature 6 weeks after June 21st. So August 1st is a good thing to know. They like to say 6 weeks after June 21st. When does the lowest temperature occur? Well, here you could see the lowest amount of insolation, minimum insolation. And then they show you the minimum temperature right here. The minimum insolation is December 21st, the winter solstice. But the minimum temperature, that actually occurs right here about February 1st. Reason being, again, the ground is just getting colder and colder. You might have some snow cover too. And that is why February here, late January into February, is usually when we get our biggest snowstorms. It is just a colder time of the year. So why does this happen? It's the same explanation. Earth's surface absorbs a great amount of radiation in May and June and then releases it by the first week of August. You're getting hit with that 1-2 punch 6 weeks after June 21st. Now, lastly, let's talk about global warming. Global warming is such a hot topic, again, no pun intended, but the reason is it is happening. I know some people say it's not, but it is indisputable. You look at the temperatures over the last 40 years, 50 years, we are going up, and sure, we always go in cycles, but we are going up at a rate that we've never seen before. And there are two reasons for this. And this was in the news this past week, actually. The ozone layer formed the biggest hole that we've ever seen over the Arctic. And actually, because there's less traffic now with the virus and people aren't going out of their house, there's less pollution, the hole in the ozone layer actually repaired itself within about 8 weeks. So it just goes to show you we can do a lot to avoid global warming. So what is ozone? Well, eventually we're going to look next week at the layers of the atmosphere, the gases that surround Earth. And there is oxygen not only down here that we breathe, but there's also a different type of oxygen in Earth's upper atmosphere, in a layer called the stratosphere. And we breathe in a form of oxygen called O2. Ozone is actually a different form of oxygen, O3. And its primary purpose, what it does, it absorbs nearly all of those UV rays that come through from the sun. So when we actually do stuff, when we release things into the atmosphere, some of those things actually eat away at the ozone layer. And that's not a good thing. When we form holes in the ozone layer, it allows more of the UV rays to get through, and those UV rays protect Earth. And with the human activities, such as, I'm not going to say fossil fuels in this case, but maybe aerosols, stuff like that, when we form a hole in the ozone layer, we're allowing more UV rays to get through, and that is one of the reasons that we have global warming. Here's the second reason. A greenhouse. And I don't know if you've ever been in a greenhouse, but a greenhouse is made of glass. And a greenhouse, I'm sure you've heard the term greenhouse effect. So take a look at this picture here. It's a picture you do need to know. You can see the sun and those short wave rays coming down from the sun. Those short waves are your UV rays coming down from the sun. And you could see UV, or short wavelengths, are able to get through glass. Now, if you've ever been in a greenhouse, there are usually tables set up, plants growing in it, and dirt. Dirt is dark. Dirt is a rough texture. So the dirt absorbs the energy, and a good absorber is a good radiator. So you see the UV rays getting absorbed and eventually re-radiated as longer waves. This is infrared, but notice something, a big difference between infrared and UV rays. UV rays can travel through glass. Infrared gets trapped by the glass and is sent right back to the surface. So if you've ever been in a greenhouse, it is hot, it is humid, and it's not comfortable. Our atmosphere works the same way as a greenhouse. How? Water vapor is the main gas in our atmosphere. And carbon dioxide, when it combines with that water vapor, prevents the infrared rays from escaping back to space the way they should. So that activity, what activity am I talking about? I'm talking about fossil fuels. So if you've ever seen the back of a car, you see that smoke coming out from the back of the car. Those are fossil fuels, or factories that are producing fossil fuels. You just see that coming out, and you don't realize it, but it's forming a thin layer in our atmosphere that acts just like the glass in a greenhouse. And the UV rays are able to get through the layer that's formed by fossil fuels. But then when that heat energy tries to get back to space, it just hits the layer, blocks it from going back to space, and all that heat bounces back to Earth. And keep doing that over time, Earth keeps heating up. So the result is an increase in temperature on Earth's surface. So you got to remember, very important, what causes the greenhouse effect? It's water vapor and carbon dioxide. And you might even get the question, what planet actually acts like the greenhouse effect? That planet heats up big time, if they ever ask that. And I would write this down. I didn't put this in your notes, but write this down in your notes if you have them printed out, or just remember this. The planet that resembles the greenhouse effect is Venus. Love to ask that on the Regents. Okay, so hopefully that helps. And that concludes our energy unit. We're going to be able to move into weather very, very soon. So go on, you're going to do energy sheet 8, and hopefully this helps you, and good luck.